Synchronous motor is a doubly excited machine. On the stator side, we will be providing with a three-phase AC supply, and on the rotor side, we will be providing a DC supply. The three-phase supply or a polyphase supply which is given on the stator will be producing or generating a rotating magnetic field, and the speed of the rotating magnetic field is called the synchronous speed. And we have the equation for the synchronous speed as 120 F by P, where F is the supply frequency and P is the number of poles. And on the rotor side, when we provide a DC supply, there will be alternate north and south poles that are created. The working principle of a synchronous motor is that when the machine runs, the poles that are generated on the stator and that of the rotor will be locked, and this magnetic attraction will be established and will continue to run at the same speed. When an induction motor is loaded from no load to full load condition, there will be a reduction in speed. And even in the case of a DC motor, we can say, at least in the case of a series motor, there will be a reduction in speed, and even in the case of a shunt machine also, there will be a slight reduction in speed when the machine is loaded from no load to full load condition. But the speciality of a synchronous motor is that it will be running at the same speed from no load to full load condition. There will be no reduction in speed even if it is loaded from no load to full load condition. And the thing that you will have to keep in mind is, or the speciality or the change that happens in the case of synchronous motor is in load angle. When the machine is loaded, the load angle will be going on increasing, and there is a limit for load angle. And if the machine is loaded beyond a particular limit or beyond full load capacity, the load angle will be above a critical limit and the machine will be no more running, or it will come to a standstill condition. So the role of delta, the load angle, is in the case of synchronous motor, we have to consider the power transfer as well as the stability of operation of synchronous motor. The characteristics of speed versus torque or speed versus load in the case of synchronous motor will be a straight line, a horizontal line, by which we can say it is having a constant speed characteristics. We will now discuss what is the effect of load on load angle in the case of synchronous motor. In the case of DC motor, we had already seen a term which is called back EMF. Even if it is a motor, along with motoring action, in all the machines there is a generating action too. Or we can say, along with generating action, there is a motoring action too in electrical machines. For example, in the case of DC motor, we have a term back EMF, and we have the general equation that is written for terminal voltage as V is equal to EB plus IAR, where IAR is the drop in the resistance of the armature. In synchronous motor too, we can consider to have a back EMF. The armature conductors are placed in a rotating magnetic field, and because of the relative motion or the rate of change of flux linkages with respect to the armature conductors, there will be an EMF that is generated in the armature conductors that can be named as the back EMF itself. So when the machine is run by an external means, that is just for the starting mechanism, the EMF that is generated, the back EMF that is generated, as well as the voltage that is supplied to the armature winding will be equal and will be in phase opposition. The magnitude will be the same but in phase opposition. So because of that, from the diagram it is clear that there is in phase opposition and the magnitude is the same, and there will never be any resultant voltage. After synchronization, when the external VLC is removed and at the no load condition itself, even then the phasors, that is the supply voltage V and the back EMF EB will no more be in phase opposition. The angle between V, the supply voltage, and the back EMF EB will be less than 180 degree. In the diagram, in the phasor diagram that is given, it is clear that the angle is 180 minus delta 0. Delta 0 is given because it is at no load condition itself. And because of this angle difference, since it is not in phase opposition, there will be a resultant voltage that is created, that is given as ER. And because of this resultant voltage, there will be a current that is given as I0, and the angle of lag is given by theta, and it is given, the theta is given as tan inverse XS by R, and the magnitude of I naught is given as ER, the resultant voltage, divided by ZS, the synchronous impedance. If you neglect RA, the resistance of the armature, the angle theta will be equal to 90 degree. And there will be an angle between V and I naught, the supply voltage and the current, that is because of the resultant voltage, that is given as phi 0, and we can write the equation for the no load power input P0 or P naught equal to V I0 cos phi naught. At the same time, the resultant voltage, that is ER, the magnitude of the same will be gone increasing, and the angle phi, that is angle between the supply voltage and the resultant current I, will be gone increasing, and the power input that is given to the synchronous motor also will be getting increased. But during this operation, even if the load is increased, the magnetic locking will be remaining the same, or the machine will be running at the synchronous speed itself. So from the previous slide, it is clear that even if the machine is at no load condition, there is a load angle delta 0. Now consider the condition where we increase the mechanical load on synchronous motor. When we increase the mechanical load on synchronous motor, what happens is the delta, the load angle, goes on increasing. When the load on the synchronous motor increases, the load angle delta also goes on increasing. And if the machine is overloaded, that is, if the load on the machine goes beyond the rated capacity of the machine, delta also goes beyond a particular limit, that is, it goes beyond a critical value, which will cause the machine to stop or to be out of synchronism, or the machine will come to a halt, because if the load angle increases above a particular limit, the magnetic locking between the rotor and the rotating magnetic field will cease. So to conclude the discussion on the relation between the load and the load angle, we can say if the load on the synchronous motor is increased, there will not be any reduction in speed of a synchronous motor, but the load angle will be increasing and can go up to a limit or till a safer condition in which the machine will be stable. We shall analyze the phasor diagram for the synchronous motor. We will first consider the lagging power factor condition. We take V, the supply voltage, as the a reference. We have the current I lagging by an angle theta, and we have the basic equation E is equal to V minus IZS. In the case of an alternator, we have the equation E is equal to V plus IZS. The difference should be noted between the alternator and the synchronous motor. For synchronous motor, it is E is equal to V minus IZS, and in the case of alternator, it is E is equal to V plus IZS. In the case of synchronous motor, it is minus, and in the case of alternator, it is plus. It is plus IZS, and for motor, it is minus IZS. For UPF condition, I is in phase with V, and for lagging power factor, I is lagging by an angle theta, and for leading power factor, I is leading by an angle theta with respect to voltage.